Hello everyone, this is lecture 12, Applications of Determinants. In this lecture, we're going to learn a rule, it's called Grammar's rule, to help us solve a system of n linear equations with n variables. So the idea is that we're going to use determinant to help us solve the solution of system of linear equations. So we're going to derive the formula for the case of a system of two linear equations with two unknowns, and we're going to expand that for for the case of n linear equations with n variables. So first, consider the following system of linear equations of the form a11 times x1 plus a12 times x2 equal to b1. A21 times x1 plus A22 times x2 plus b2. So there are two equations, A11, A12, A21, A22 are constant, as well as b1 and b2. And the unknowns in this case are x1 and x2. And I'm going to call this equation 1, and this is equation 2. So the solution to this system of linear equation of two linear equations are already given in this case. So we can start from there, but I'm actually want to give a quick derivations, at least for the case of x2 and similar. When you have one solution, you can back substitute to either equation 1 or equation 2 to obtain the other solutions. All right, so the derivations to obtain the solutions, what I'm going to do is I'm going to use elimination method that we learned in lecture 3, I believe. So to obtain the solutions, what I do is I'm going to multiply equation 1 by a21 and equation 2 by negative a11. So I do that because I want to get rid of the variable x1. Right? So to get rid of that, I multiply the first equations by a21 and the second equation by negative a11. So when I add them together, I can eliminate one variable. All right, so doing this, we get, right, so the first equation becomes a21 times a11 times x1 plus a21 times a12 times x2 equal to a21 times b1. That's from the first equations. Now for the second equations, I get negative a11 times a21 times x1 minus a11 times a22 times x2 equal to negative a11 times b2. Right, so we obtain two equivalent equations from the first equation and the second equations. The next step is to combine or add these two equations together to get rid of the variable x1. So add the two equations. We obtain the following. Right. So when you add these two equations together, what we have is that this term and this term will cancel out automatically. And you're left with the following terms on the left-hand side. A21 times A12 x2 minus A11 times A22 times x2 equal to the right-hand side, which is A21 times B1 minus A11 times B2. And at this point, actually, let me rewrite this. This is x2. So at this point, what you can do is that on the left-hand side, you take x2 as the common factor, and you're left with x2 times a21 times a12 minus a11 times a22 equal to a21 times b1 minus a11 times b2. And you can divide both sides for this term to obtain the representations of x2. So x2 is equal to a21 times b1 minus a11 times b2 divided by a22 times A12 minus A11 times A22. Right. So either you can stop right here for x2, but I want to actually rewrite the solution I just got a little bit so it match with the solutions I already wrote down at the beginning, right? So what I'm gonna do is just multiply and divide it by -1 of multiply on -1 on the numerator and -1 on the denominator. At the same time, I just try to switch the sign a little bit. So x2 becomes A11 times B2 minus A21 times B1 divided by A11 times A22 minus A21 times A12. So that's the solutions x2, right? And to obtain x1, again, what you do is you back substitute x2 into either equation 1 or equation 2 to obtain the representations of x1, right? So the procedure is to back substitute x2 into equation 1. You can substitute back into equation 2, doesn't matter. So we're going to get here. I'm not gonna spend time to derive x1 anymore. I'm just going to copy the value of x1 from what we have up here, right? It's going to be just a few manipulations to get x1. So x1 is equal to B1 times A22 minus B2 times A12 over A11 times A22 minus A21 times A12. For these two solutions, what you need to have is that, the denominator cannot be equal to 0. So that is the conditions that we need to impose. A11 times A22 minus A21 times A12 has to be equal to 0. If it's equal to 0, it's not going to work, right? The solution does not exist. So we have to impose that conditions. Now, what is the reason for this two solutions in kind of the general or the generic way of writing a system of linear equations, right? Just the letters. Right? The idea is that if you notice x1 and x2, the numerator and the denominator of the solutions, is can actually be written as the determinants of a 2x2 matrix. Right? So for x1, right, what you can do is that the numerator is actually equal to the determinant of the form B1, A12, B2, A22. Right. So now if you compare the numerator we got here with the numerator in terms of the determinant, right, you can see that to calculate the determinant, the product of the main diagonal B1 times A22, B1 times A22, minus the product of the off diagonal. Right, so minus the product B2, A12. Now in the denominator, that is the determinant of the form A11, A12, A21, and A22. So basically, this is the determinant of the coefficient matrix from you obtain from the system, right? So the coefficient matrix right here, use them in here a little bit. So A11, A12, A21, and A22. So that is the coefficient matrix. And what we got in the denominator here is the determinant of that coefficient matrix. So there's a reason that's why we want to write the solution in this way, so that we can obtain something that is useful for us in terms of calculating the determinant to obtain the solution of the system. All right, similarly for the case of x2, so x2, now if you consider the numerator, right, is actually equal to the determinant of the form A11, B1, A21, B2. All right. And the denominator is going to be the same as in the case of x1. So a11, a12, a21, and a22. All right. Now, if you let the capital A be the coefficient matrix of the system, right, you get that the denominator for this solution is going to be the determinant of A. Here, the determinant of A. Okay. And the numerator, now I need your attention here. The numerator, you see that this determinant, if you replace the first column by the entries from the right-hand side of the system, right? The right-hand side of the system is B1, B2. If you remove the first column of the coefficient matrix and replace that with the entry from the right-hand side, right, you obtain this particular determinant, right? And because of that replacement, we call this the determinant of A1, right? For A1 is equal to this following matrix B1, A12, B2, A22, right? Now for the second solutions, right? If you, from the coefficient matrix, if you remove the second column and replace that with the entry from the right-hand side, you obtain this particular matrix or the determinant of this matrix. And because of that, I'm going to call this the determinant of A2. For A2 is equal to the matrix of the form A11, A21, B1, B2. Okay. And of course, from here, you can use it to calculate the solutions, but through the lens of the determinants of matrices. Okay, which is in a way is very useful, especially if you know how to code this up. It's it's a very fast way to obtain the solution of system. Right, you don't have to do Gauss-Jordan eliminations. You don't have to find the inverse of the matrix. You just need to find the determinant of the matrix. Right, it's a lot easier to deal with. Okay, so let's use this formula, right, for the case of the system of two linear equations with two unknowns to obtain the solutions of the following system. Right, so you have the system of the form 4x1 minus 2x2 equals to 10, and 3x1 minus 5x2 equal to 11. Now, the coefficient matrix from this given system is, so the coefficient matrix is A equal to 4, -2, 3, -5, right? So x1 is equal to the determinant of, let me be careful here. So the determinant of A1 divided by the determinant of A. For A1 is of the form. So in the coefficient matrix, you remove the first column and replace that with the entry from the right-hand side. So let me use the red pen here. So the first column becomes 10, 11, and the second column remains the same, which is -2, -5, and divided by the determinant of the coefficient matrix for -2, 3, -5. So let's calculate this solution. So this is the 2 by 2 determinant. So I have 10 times -5 minus 11 times -2 divided by the determinant of A, which is 4 times -5 minus 3 times -2. Now, if you do the calculations correctly, what you're going to get is on the numerator, you have -28, and in the denominator, you have -14, while this is equal to +2 for that matter. Okay. Now that is x1. For x2, yeah, this is equal to a determinant of A2 divided by the determinant of A. given that A2 is going to be, right? For A2, you remove the second column of the coefficient matrix and replace that with the entries in the right-hand side. So the first column remains the same. The second column now becomes 10, 11. All right, and you divide it by the determinant of the coefficient matrix for -2, 3, -5. This is equal to 4 times 11 minus 3 times 10 over, right? So we already calculated the determinant of A, which is going to be -14. The numerator becomes +14 and divided by -14, you have -1. Therefore, you say that the solution of the system is, you can say that x1 equal to 2 and x2 equal to -1. So that's Grammar's rule for you, right? It's help us to calculate the solutions of the system using determinants. Now we're going to generalize this rule, right, for the case of n linear equations with n variables. So if a system of n linear equations in n variables has a coefficient matrix A with non-zero determinant, then the solution of the system is right, so you get x1 equal to the determinant of A1 over and the determinant of A, x2 is equal to the determinant of A2 divided by the determinant of A, so on and so forth until the last solutions is x sub n equal to the determinant of A sub n divided by the determinant of A. Remember, for A1, you remove the first column of A and replace that with the right-hand side. For A2, you remove the second column of A and replace that with the right-hand side. And for A sub n, you remove the n column and replace that with the right-hand side. Right, so hopefully that makes sense to you. And then you calculate the determinant of A1, A2, so on and so forth, and divide that with the determinant of A to obtain the solution x1, x2 up to xn. So now in the following example, I have a system of 3 equations with 3 unknowns, x, y, and z. So I'm going to write down the coefficient matrix here. And the matrix is of the form -1, 2, -3. And the second row is 2, 0, 1. The third row is 3, -4, +4. Okay. So you have 3 equations with 3 unknowns, x, y, and z. So you need to form A1, A2, and A3. Right. So for A1, right, so A1, so you remove the first column of A and replace that with the entry of the right-hand side. So the right-hand side now becomes 1, 0, 2. That's the first column. The second column is 2, 0, -4, -3, 1, 4. Right. So A2 is, it has the form Right, so for A2, you remove the second column of A and replace that with the entry of the right-hand side. So -1, 2, 3. So the first column remains the same. The second column becomes 1, 0, 2. And the third column is -3, 1, +4. And for A3 is what you get. So the first and the second column remains the same. So -1, 2, 3, 2, 0, -4. And the third column now gets replaced by the entry of the right-hand side, so 1, 0, 2. So the solution of the system is you have x equal to the determinant of A1 divided by the determinant of A. Y is equal to the determinant of A2 divided by the determinant of A. And Z is equal to the determinant of A3 divided by the determinant of A. So now let's calculate the determinant of A1. So the determinant of A1 is 1 to -3, 0, 0, 1 to -4, +4. All right. So for this 3 by 3 determinants, right, you can calculate the minors and then the corresponding cofactor, or you can just use the formula. Sorry, this is 4. Right. So use the formula that I'm going to use the second row. So A21 times C21 plus A22 times C22 plus A23 times C23. Given that this term is going to be equal to 0, this is going to be equal to 0 because A21 is 0, A22 is 0 as well. Now for A23 is equal to 1, the corresponding minors of C23 is going to be, or C23 is going to be equal to, let me look up the sign, so positive, negative, positive, negative. So this is going to be equal to negative of A23 times M23, or -1 times. And so if you take this entry, delete the corresponding column and the corresponding row, you're left with the entries of 1, 2, 2, -4. So this is negative of -4 minus 4. This is equal to +8. Right, so that is the determinant of A1. Now for the determinant of A2, right, you get this is -1, 1, -3, 2, 0, 1, 3, 2, 4. I'm going to still use this second row to work with. So you get A21 times C21 plus A22 times C22 plus A23 times C23. And we know that this term is going to be equal to 0 because A22 is equal to 0. Now for the cofactors, the corresponding minors, so it's going to be, so we start with plus, minus, so this is 2 times negative M21, right? 2 because A21 is the entry, this entry. So this is plus, minus, plus, minus. So you have -1 times C23. Sorry, so let me be careful here. So plus 1 times negative M23. Okay. Or this is -2 times So you select this entry, delete the corresponding column and the corresponding row. You're left with the entry 1, -3, 2, 4, minus -2, 3. So you choose this entry, delete the corresponding column and the corresponding column row, and you're left with the entry of -1, 1, 3, 2. So you get -2 times 4 minus -6 minus -2 minus 3. If you do the calculations correctly, you will get -15 for the answer. Now for the determinant of A3, you get, this is -1, 2, 1, 2, 0, 0, and 3, -4, +2. Right. Still, I'm going to use the second row to work with, right? Because you have 2, 0 in that particular row. So A21, C21 plus A22 times C22 plus A23 times C23. And we get that this term is going to be 0. This is also 0 as well. The entry of A21 is 2, right? And C21, corresponding minor is going to be -M21, or -2 times, right, to this entry, delete the corresponding column and the corresponding row. You're left with the entry of 2, 1, -4, 2. What is -2 times 4 minus -4? Well, this is going to be -16. And the solutions of the system becomes that x is equal to determinant of A1 over A, or this is 8 over 10. You simplify that, you get 4 over 5. Y value is the determinant of A2 over the determinant of A, or this is -15 over +10, or you simplify it, you get -3 over 2. And the value of z is the determinant of A3 over the determinant of A. You get -16 over 10, or this is -8 over 5 for simplifications. So that's it for me for this lecture. In this lecture, we learned about Cramer's rule, right? Another way for us to solve the system of n linear equations with n variables. And you obtain the formula of this form, right? If you have the first component of the solutions is equal to a fractions of the determinant of A1 over the determinant of A. The second component is the determinant of A2 over the determinant of A, so on and so forth, given that capital A is the coefficient matrix of the system. And A1 can be obtained or can be formed by removing the first column of the coefficient matrix and replace that with the entry in the right hand side. And A2 can be formed by removing the second column of A and replace that with the right hand side of the system, so on and so forth. Right, so that is the Cramer's rule. That's it for me. Please let me know if you have any questions. Thank you.